Deep neural networks, DNNs, rely heavily on mathematical concepts and operations to perform their tasks effectively. Understanding the underlying mathematics is essential for designing, training, and fine-tuning these networks. Here are some fundamental mathematical concepts and operations involved in DNNs. Pradeep K. Suri. Author and researcher. 1. Linear algebra. Vectors. Vectors are used to represent input data, weights, and activations in DNNs. Matrices. Matrices are used to represent the connections between layers, including weight matrices and activation matrices. Matrix multiplication. The dot product of matrices is used for forward and backward passes through the network, including calculating activations and gradients. 2. Calculus. Derivatives. Calculus, particularly derivatives, is crucial for gradient descent optimization algorithms used to train DNNs. It helps in computing gradients for weight updates during backpropagation. Chain rule. The chain rule is applied during backpropagation to compute gradients of composite functions, which is essential for updating weights efficiently. 3. Activation functions. Sigmoid. The sigmoid function maps real numbers to the range 0, 1, and is used in older neural network architectures. ReLU, rectified linear unit. The ReLU function is widely used in modern DNNs due to its simplicity and effectiveness. It is defined as f x equals max 0 x. 4. Loss functions. Mean squared error, MSE, used for regression tasks. It measures the difference between predicted and actual values. Cross entropy, commonly used for classification tasks. It quantifies the dissimilarity between predicted and actual probability distributions. 5. Gradient descent. Gradient. The gradient is a vector of partial derivatives with respect to the model parameters. It points in the direction of the steepest increase in the loss function. Learning rate. Learning rate is a hyperparameter that controls the step size during gradient descent. Proper tuning is essential for convergence. 6. Backpropagation. Backpropagation is a recursive application of the chain rule, allowing the network to compute gradients of the loss function with respect to its weights layer by layer. 7. Optimization algorithms. Stochastic gradient descent, SGD, an optimization algorithm used to minimize the loss function by adjusting the model parameters in small steps. ADAM, RMSprop, ADAGRAD, variants of SGD with adaptive learning rates, often used for faster convergence. 8. Regularization techniques. L1 and L2 regularization. These techniques add penalty terms to the loss function to prevent overfitting by encouraging smaller weights. Dropout. Dropout randomly drops neurons during training to reduce overfitting. 9. Convolution. Convolutional neural networks, CNNs, use convolution operations to extract features from input data, particularly for image and spatial data. 10. Matrix factorization. In recommendation systems, matrix factorization techniques, such as singular value decomposition, SVD, are used to uncover latent factors in user-item interaction matrices. 11. Statistics. Statistics play a role in data pre-processing, feature scaling, and the evaluation of model performance through metrics like mean and standard deviation. 12. Probability. Probability theory is essential in understanding and designing probabilistic models, such as Bayesian neural networks and probabilistic graphical models. 13. Information theory. Concepts from information theory, such as entropy and KL divergence, are used in designing loss functions and understanding model uncertainty. 14. Eigenvalues and eigenvectors. These concepts are involved in various linear transformations and dimensionality reduction techniques like principal component analysis, PCA. Deep neural networks leverage these mathematical principles to model complex patterns and relationships in data, making them powerful tools for various AI and machine learning tasks. Understanding the mathematical foundations allows practitioners to effectively design, train, and fine-tune DNNs for specific applications. Thank you.